How are you doing here? This is Mike again, and in this video, this will be the last video that I have on graphing polynomials, and we're going to be sort of concluding this with some more advanced polynomial circumstances. In the past videos, we've talked about leading term behavior, we've talked about the zeros and their multiplicities, and now we're just bringing it all together into one section and determining how to give a possible graph, not necessarily the exact graph, but a possible graph of a polynomial. So let's go ahead and try a new example that's slightly different than what we did in our last video. So let's say that we have x minus 2 squared times x plus 4 cubed. So we have x minus 2 squared times x plus 4 cubed. This is a polynomial, and we recognize we have no rational values, we have no variables in our denominator, and we don't have any radicals. So we're pretty safe to say this is a polynomial. The first thing we're going to have to do is identify our leading term. When we talk about how to identify our leading term, this could be a little bit more complex. So some people do it a couple different ways. I'm going to show you a little trick. Here. So notice, if I were to expand out x minus 2 squared, I hope you guys all agree this would be x squared minus 4x plus 4. That one I have memorized. I've done it quite a few times. If we were to expand out x plus 4 cubed, let's go ahead and show you what that would be. That would be x plus 4 times x plus 4 times x plus 4. Okay. Folding these two out together, we're going to have x squared plus 8x plus 16 still times this guy, which is going to be a value of x plus 4. X squared times x gives me x cubed. X squared times 4 gives me 4x squared. 8x times x gives me plus 8x squared. 8x times 4 gives you plus 32x. 16 times x gives me plus 16x. And then 16 times 4 gives me a value of 64. So combining my similar terms, I'm going to have 8x cubed. 4x squared plus 8x squared gives me 12x squared. 32x plus 16x gives me a value of 48x. And then lastly, I'm left with a value of 64. And I say, oh my goodness, I haven't even started the problem yet. I've just go ahead and been expanding everything. So I will show you a trick. Notice, if we were to multiply every single one of these terms together, I hope we would all recognize that our most important one when it comes to leading term analysis is our leading term, or the term with the largest degreed exponent. So notice, if I'm going to multiply this together ultimately first, I would have x squared times x cubed, which would give me a value of x to the 5th. I don't care about all the rest of those for leading term analysis. All I care about is the leading term. So my leading term here is in fact a positive x to the 5th, which we could have determined by getting the x squared here and multiplying times x cubed here. Remember, when I have two of the same bases multiplied together, I add their exponents. So 2 plus 3 gives me a value of 5. So my leading term here for this polynomial is a positive x to the 5th. Drawing this potential graph, I know I'm going to start down here in quadrant 3. I don't know what's going to go on in the middle at this point, but I'm going to exist and keep on going until quadrant 1 because I have a positive coefficient and an odd exponent. So now I can go ahead and I can, in my second step, identify my zeros. That shouldn't be apostrophe, it should be just zeros. And then I can also identify my multiplicity on the way. So I like to do these simultaneously, but this right here is going to give me that leading term, and it's a nice trick that I can use to be a little bit more expeditious with these problems. So now we want to set my polynomial equal to 0 in order to find those zeros. So I'm going to get x minus 2 squared equals to 0, and then I get x plus 4 cubed equals to 0. So I'm going to go ahead and I like to identify my multiplicities because they're going to be indicated by the degrees of the terms that give you those zeros. And now we can go ahead and we can solve these. So we would actually raise both sides to the 1/2 power. Ultimately, we would get x equals to 2. I feel safe at this point that you can solve this. And we would raise this to the 1/3 power, and ultimately we get x equals to -4. So I feel pretty safe at this level we can solve those equations. Now I like to indicate my multiplicity, which I abbreviate MP. My multiplicity of this 0, which is 2, is equal to 2, and that's an even value. Therefore, I know my action is just going to touch. Because I have an even multiplicity, I'm just going to touch at the 0. And then over here, I have a multiplicity that's equal to 3, and I know that's an odd value, so I know at this 0 I'm going to cross. So now I know my zeros, their action, and I know my leading term analysis. So let's go ahead now and draw a potential function. Let's go ahead and draw a potential function. So I'm going to indicate my zeros first. So I got 1 at -4, I know I'm going to have a 0 there, and then I have 1 at +2. So I have -4, and then I have +2. I'm going to go ahead first and look at my leading term analysis. And notice I'm going to start down here in quadrant 3, and I'm going to end in quadrant 1. So I'm going to start down here at quadrant 3, and I better end in quadrant 1. If I don't end in quadrant 1, something is wrong. So I should end up here. I should end up here. So let's see what happens at -4. At -4, I know I'm going to cross the x-axis. So over here at -4, I'm going to come on up, and I'm going to cross the x-axis. And then I'm going to continue on. I know I have to either touch or cross 2. And notice I just touch it 2. So that means I come over down here and I touch it 2, and then I bounce off. And notice I come out to where I want it to be. So I feel very safe and confident that this is a good graph, a good potential graph of my function. Let's go on and try another example. Let's go ahead and try one more example in this video. And let's say that I want to graph the function, or give a potential graph of the function, -x² times x minus 3 squared times 2x plus 1 to the 4th. So that's 2x plus 1 to the 4th. There we go, 2x plus 1 to the 4th. The first thing is we want to do before is that we want to identify our leading term. Our leading term. So be very careful here, ladies and gentlemen. My leading term from this first term is going to be -x². I would have to multiply that times the leading term of this polynomial if I expanded that, and that would also be a value of x². And then the leading term of this polynomial would be a value of 2x all to the 4th. 2x all to the 4th. So be very careful because it's the quantity of 2x. This still gives me that -x². This gives me this +x². 2 to the 4th gives me a value of 16x to the 4th power. Because 2 times 2 is 4, times 2 is 8, times 2 is 16. We have to raise 2 to the 4th and x to the 4th. So notice now, since I am multiplying my similar bases, I can go ahead and add their exponents. So I'm going to have a negative and a positive and a 16. Multiplying those together, I get -16. x² times x² gives me x to the 4th, times another x to the 4th gives me -16 x to the 8. So x to the 8th. So my leading term here is going to be -16 x to the 8th. So now I recognize I like to draw a potential picture of my leading term analysis. So I know that since I have an even exponent and a negative leading coefficient, I'm going to open down and end down. So I don't know what I'm going to do in the middle at this point, and then I'm going to come on here and end down. So I start in quadrant 3 and I end in quadrant 4 because I have an even exponent and I have a negative leading coefficient. Now I'm going to go ahead and set each one of these factors. Well, I'm actually going to set my whole polynomial equal to 0. So I get -x² equals to 0. I get x minus 3 squared equals to 0, and that's a squared. And then I get 2x plus 1, I don't know why I have a problem drawing that, to the 4th equal to 0. I'm going to go ahead now at this point, I'm going to identify my multiplicities by putting an orange box around them so that way I don't forget what they are later on as I solve. Solving my first equation, I know that we should feel confident at this point that I'm going to get x equals to 0. Solving my second one, I'm going to get x equals to 3, and I'm going to go ahead and do this next one out. So if I want to solve 2x plus 1 to the 4th equaling to 0, to the 4th equals to 0. I don't know why it combines. I guess the computer thinks that, or the program thinks that I meant to attach those values. So now I'm going to raise both sides to the 1/4 power. And that's a 1/4. It's just, it's annoying. So the 1/4 power. And the 4 and the 1/4 multiply together give me a value 1, so I get 2x plus 1 equals to 0, because 0 to the 1/4 is 0. I subtract 1 on both sides, and I get 2x equals to -1. Divide both sides by 2, and I get x equals to -1/2. So now I know that I have I have 3 zeros. I'm going to identify their multiplicities and their actions. So their multiplicities of this first 0 is a 2, which is even. Therefore, I have an even multiplicity, so I expect to just touch. Here I have a multiplicity of 2, which is also even, so I expect just to touch at this 0 as well. And then over here I have a multiplicity that's equal to 4, which is even, and another even multiplicity means I'm just going to touch. So I'm touching at each one of those zeros. I do not cross anywhere on my axes. So let's go ahead now and draw a potential curve using my Cartesian plane. So I'm not going to draw this as scale. I just want to indicate the pragmatic parts. So notice here I'm going to distinctly move my -1/2 down here. This will be -1. This will be 0. And then my last 0 that I see here will be at +3. So I'm just trying to indicate I'm not drawing this to scale. And I recognize that I have a 0 at 0. I have a 0 at 0, so I'm going to shade in a 0 here. I have a 0 at 3, so I know I'm going to have a 0 here. And then I have a 0 at -1/2, so I have a 0 here. Based off my leading term analysis, I know I'm going to start off in quadrant 3 and end in quadrant 1. I'm sorry, end in quadrant 4. So starting off at quadrant 3, I know that I'm just going to touch at -1/2, bounce back off. I'm going to touch at 0, bounce back off, and touch at 3, and bounce back off. And we're going to get something that looks like this. And again, this is not drawn to scale. We are just simply identifying a possible and potential functional graph for the polynomial that was given. So with all of these, you can verify by graphing these on the graphing calculators. However, that is not as important to us because we're just looking for those important facets of determining the action at the zeros, and then also determining the behavior as we approach positive infinity, as we approach negative infinity.